So our first speaker this afternoon, or in the second session of the afternoon, I suppose, is María José Sánchez Rincón, who's joining us from Caltech. Maria's been working this summer with Mandy, and today she'll tell us about their project together, probing the dynamics of the circumgalactic medium around UGC 7342.
Okay, thank you, Gwen, for that introduction. I'm glad I'm able to present even if it's from a distance, so let's just get right into it. So what is UGC 7342? This is a galaxy located in the Coma Berenices constellation, and it has been confirmed to host an active galactic nucleus in the middle, which just means that it hosts a supermassive black hole at the center. This galaxy is at a redshift of z equals 0.0477, which is relatively low for galaxies that we study, although keep in mind this is only relatively. The galaxy is still moving away from us at approximately 14,000 kilometers per second due to the expansion rate of the universe, and it is also approximately 600 million light years away. And the 2020 Decadal Survey of Astronomy and Astrophysics called Unveiling the Drivers of Galaxy Growth and Evolution a priority area of research in astrophysics, which is why we wanted to investigate this galaxy. Very little is known about the dynamics of the gas within the galaxy's circumgalactic medium. And this project aims to probe the dynamics and constrain the velocities present in the galaxy. For example, we aim to extract the brightness of the circumgalactic medium, which I will explain shortly what it is, model its spectrum, constrain the velocities, and probe the turbulent motions. So, what is a circumgalactic medium? I want to first zoom out and just look at this image right here, which represents the cosmic web, which is basically a diagram showing that galaxies are connected through gases no matter how far away they are from each other. And if we zoom into one of these dense white areas, we would see the circumgalactic medium of a galaxy. It is the outermost layer, the outermost gaseous halo of a galaxy that is beyond the interstellar medium, which is where stars usually lay. And this circumgalactic medium, or CGM for short, is still gravitationally bound to a galaxy, although even if it's hundreds of parsecs away from the interstellar medium. And as you can see, there is many processes going on in the circumgalactic medium. For example, the recycling of gases called the baryon cycle of a galaxy. There is outflows of gas due to interactions with outside galaxies, and also the inflows of gas due to the host galaxy's gravitational pull. And in the circumgalactic medium, there is many ionized gases present due to the heat of the circumgalactic medium. So, what can we extract from the CGM? So, outflows of the galaxy, which are usually due to the active galactic nucleus in the middle, inject kinetic energy into the circumgalactic medium. And therefore, the motions of gas begin as a bulk flow or laminar flow. As you can see in this diagram, there is big areas of laminar flow in this circumgalactic medium. But as time goes on and you zoom in, you begin to see these small eddies or whirlpools of turbulent motion. And as we zoom in even closer, this turbulent motion stops due to the viscosity of the gas and instead dissipates in the form of heat to conserve energy in the circumgalactic medium. This turbulent flow therefore creates a multi-phase gas, which basically just means that there is various temperatures of gas, there's various densities, and also various ionized gases present within the circumgalactic medium. So, how do we probe these dynamics? So we started with data from the multi-unit spectroscopic explorer on the Very Large Telescope. This instrument presents data in the form of a 3D data cube, which is called an integral field spectrograph. The dimensions of this three-dimensional data set is right ascension in the sky, the declination in the sky, and the wavelength. So basically, just to visualize, this data cube gives you an image of the flux at every wavelength that we're concerned with, which in this case was from 4,600 angstroms to 9,300 angstroms. Just to visualize it, this image is looping through different wavelengths, and you can see two prominent peaks in flux compared to the background. And these represent us looping through the O3 doublet spectrum. This is the flux of just one pixel in this image. And if you note, there is a 324 by 322 dimension to this data set, which means we're working with about 104,000 spectra, which is a lot, but soon I'll explain how we reduced it to a much smaller number. So, what did we first start off doing with this data? We first did something called continuum subtraction and narrowband imaging. Continuum subtraction is when you have a spectra of this sort, and if you look closely on the flux axis, you'll see that the spectrum is centered around the 50 line on the flux y-axis. We don't want this because a narrowband image sums under the curve, and this continuum is some extra brightness that is caused either by an active galactic nucleus, a quasi-stellar object, or just a bright object in the background of the circumgalactic medium. So what we first did was interpolated a line that allowed us to subtract this extra continuum and shift the spectra down to the 0 line. This then allowed us to loop through every pixel and sum under the curve in order to get the brightness measurement. And after doing this for all our pixels, we managed to create some brightness maps. The middle bottom one is the one created with this spectrum specifically, and the ones on the right-hand side for H alpha and N2 was just the same process, but we just did it for the H alpha emission line and the N2 emission line. It's the same process and we loop through every pixel. And the main purpose of this, I want you to note on these brightness maps that the O3 is the brightest emission in our circumgalactic medium, but I also want you to note that this is a relative brightness, a relatively high brightness, because any factor assigned to the brightness is multiplied by a factor of 10 to the negative 20, which shows how diffuse and dim the gas around the circumgalactic medium is. It's thanks to instruments like MUSE on the Very Large Telescope that were able to probe this gas when we couldn't decades before. So, after this, we moved on to the MCMC Gaussian model fitting. Basically, we just want to fit a bimodal Gaussian to our spectra to be able to extract the redshift of the spectrum. So, first, with our brightness maps, we created a signal-to-noise ratio cleaning, which just means we eliminated points with either a weak emission or no emission, and that left us from 104,000 spectra to fit to only about 35,000 spectra to fit, which is still an immense number, which is why we were working with high-performance computers for this step. So after this, we started the MCMC run. Some of our free parameters were the redshift z, the width, and the amplitude of the Gaussian. And we chose the redshift z instead of the center of the two Gaussians because the redshift z should be the same for both of the Gaussians, no matter where the center of it is. So after about 35,000 spectra and about 30 or more hours of running code on the HPC, we were able to fit the spectra to a Gaussian model. As you can see on the left-hand side is a corner plot showing the MCMC chains converging to certain values that it believes to be the best parameter for our spectrum. And to the right, you can see the Gaussian fit modeled over the original data, and it shows that it agrees to a very high percentage. So, of course, we also kept in mind cleaning any chains that were not a good fit in order to preserve accuracy. So after this step, the most important thing we wanted to extract from the MCMC run was our velocity maps. And with the redshift z, we also had to keep in mind, as I mentioned previously in my first slide, we wanted to remove the intrinsic velocity of the circumgalactic medium as it moves away from us due to the expansion rate of the universe, that 14,000 kilometers per second. We want to only see the velocity in the rest frame, and that's exactly what we did when we created these line of sight velocity maps. As you can see, we're also able to make a velocity uncertainty map thanks to the MCMC run giving us uncertainty measurements, and we were able to eliminate any points in this map that had an uncertainty of plus or minus 30 kilometers per second. And then an additional step we took in mind was to create the gradient map, the gradient velocity map. This gradient velocity map basically just maps the bulk flow of the galaxy, which we do not concern ourselves with, and we subtracted it from the line of sight velocity map. So why do we want to remove this gradient from our velocity map? As I said, it helps remove the bulk velocities and helps us isolate the turbulent velocities in the circumgalactic medium, which was the goal of this project. And then it also helps us improve our velocity structure function, which is our next step in our project. So, a velocity structure function, what exactly is it? It is dictated by this equation on the bottom right-hand corner, and the plots look like this. Just to give you a visual interpretation of what this velocity structure is and how it is plotted, just imagine if you choose r equals 14 kiloparsecs, and you begin to find every point in this galaxy that is distance that is equally spaced apart at 14 kiloparsecs, find the difference in velocity between those 2 points, square that value, and then find the average of all of those points on this galaxy. We iterated over this equation from r equals 1 to about r equals 60 kiloparsecs, and after that we didn't want to go any higher because there is very few points in our circumgalactic medium that are distanced apart 60 kiloparsecs. So, as you can see on our graphs, there is an orange dotted line, which is the 2/3 power law slope. Why do we have that on our graph? This is due to the Kolmogorov turbulence. Kolmogorov turbulence, a type of turbulence that is homogeneous, isotropic, and an incompressible flow, tells us that if this type of turbulence is present in our circumgalactic medium, the velocity structure function should scale as r to the 2/3 power. The reason that we wanted to graph this is because my mentor Mandy Chen was able to find some circumgalactic mediums that agreed very highly with the Kolmogorov turbulence power law slope. But as you can see, both of our velocity structure functions did not agree with this slope. But there is many more things to extract from these velocity structure functions. So for example, it not scaling with the 2/3 power law indicates multiple factors affecting the circumgalactic medium. For example, the active galactic nucleus can be ionizing the gases. There can be tidal interactions between other neighboring galaxies, no matter how far away they are. And there could also be local shock regions or compressed regions of gas, which do not line up with the definition of Kolmogorov turbulence. And I just want to take a second to really grasp the fact that an active galactic nucleus that is in the center of a galaxy can affect something hundreds of kiloparsecs away. And also the fact that galaxies millions of light years apart can still affect each other, as we can see through the cosmic web diagram. I think that's pretty amazing. And another thing we extracted, if we take a look at the right velocity structure function, we see that there is a flat trend from the 6 to 20 kiloparsec area. In velocity structure functions of the second order, this is an indicator of an energy injection scale. This just means that gas is not behaving turbulent at this scale because energy is still being injected and the gas is barely starting to move in a bulk or laminar flow. Of course, this is only a first look into the galaxy circumgalactic medium, and it is only one form of probing it by using a velocity structure function. But it's a very good first look, and of course, there would have to be other tests ran to really conclude many things. So one thing that we can say with for sure is that the circumgalactic medium dynamics show signs of having multiple factors affecting it. It is not an isolated system, and we can clearly see that the circumgalactic medium does interact with both the interstellar medium of the galaxy and other galaxies around it, no matter how large these scales are. But to truly analyze these complicated structures, we need to look more into more probing methods. For example, some future steps could be comparing gas near the active galactic nucleus to gas far away from the active galactic nucleus and seeing how the AGN differs in its effects to the circumgalactic medium. Another one would be locating high ionization regions in our circumgalactic medium by plotting the ratios of different emissions. But of course, my project was only a first look and we're really happy with the results we had. So I just want to thank my mentor, Mandy Chen, for this amazing first research experience and the CASI cohort for being such a great time. Thank you, and I'm happy to take any questions.
All right, thank you, Maria. Do we have questions?
Hi, Maria. Can you just clarify something I might have missed? That when you were running your MCMC sample, I saw that you had the redshift parameter free, but I'm also aware that we know the redshift to a large extent. So is that to clarify just like the local, is that something you're using to find the radial velocities? And am I
Yeah.
on the right track?
Yeah, that's a good question. So yes, we know the bulk redshift of the galaxy, which is the 0.0477. But if you look at the data, there is small deviations in where the emission line is found. Those tiny little deviations in the redshift in the center of the wavelength do correspond to the radial velocity of the galaxy in the rest frame. And this MCMC was used to be extremely accurate because this shift in the wavelength emission can be on the order of a few tens of angstrom. So it needs to be very accurate, and from there we're able to extract the rest frame radial velocities.
Okay, thank you.
Mm-hmm.
Other questions?
Amazing presentation, Maria. So I think I didn't understand in the previous slide, when you subtract the gradient, what's the significance of it and how does this help with the velocity structure function?
Oh, yes. So subtracting the gradient just helps us remove any bulk velocities from the galaxy. Because at some point, you can kind of see in our first line of sight velocity that there is this sort of gradient going from a negative radial velocity to a positive. This basically is just the bulk flows or laminar flows still present in the circumgalactic medium. And our project did not want to work with those. So you model the gradient in the background of the circumgalactic medium and remove it to be left with what we believe to be only turbulent velocities in the galaxy. And even then, comparing the line of sight velocity, initial velocity graph, with the final one, you can see that there's already some sort of smaller eddies of motion in the circumgalactic medium compared to our original line of sight velocity.
That makes sense. Thank you.
Yeah.
All right, any other questions for Maria? Oh, one more.
Thank you for your presentation, Maria. It was really cool. I was wondering what are some of the, you talked about next steps of further analysis to confirm some of the theories that you had. I was wondering what some of those next steps might be. Are there specific other things that you want to check for?
Yes, so one of the challenges that I didn't have time to mention was creating a BPT diagram, which basically means it's a plot that marks the O3 emission ratio with the H beta on the y-axis and the N2 emission with the H alpha ratio on the x-axis. This is called a BPT diagram, and by looking at where most points lie on this graph, you can check how ionized gas is at certain regions, and you can do something that's called spatially resolve it. So you can map any point on this graph to any point on the original image of the galaxy, and from there you can locate where there is the most ionized gas, for example, the O3 gas, and it can help you show what parts of the galaxy are like the most active with like higher energy input or hotter. That would be some next steps that we unfortunately did not have time to get to, but that would really help us probe the circumgalactic medium to a better extent.
All right, let's thank Maria again.
Thank you.